Imagine traveling through space, leaving Earth, leaving the solar system, leaving the galaxy, watching the stars thin out behind you until there is nothing ahead and nothing behind and nothing in any direction for hundreds of millions of light years. No planets, no gas clouds, no lone drifting atoms. Just cold, expanding darkness with no end in sight.
These regions are called cosmic voids, and they are the closest thing the universe has to true nothingness.
But nothingness, it turns out, has a lot to teach us. To understand voids, you first need to see the universe at its largest scale, and at that scale, the universe looks nothing like you'd expect. Zoom out far enough, and the billions of galaxies don't scatter randomly like dust on a dark floor.
Instead, they form a vast three-dimensional web, a structure astronomers call the cosmic web, where galaxies cluster along long filaments of dark matter that stretch across hundreds of millions of light years, connecting at dense intersection nodes called galaxy clusters.
Picture a sponge, or better yet, picture soap foam in a bathtub, thin walls surrounding large bubbles of empty space. Galaxies live on the walls. The bubbles are the voids. This pattern wasn't obvious for most of human history because you can only see it by mapping millions of galaxies simultaneously, which required telescopes and computers we only recently built. In the 1980s, when astronomers first mapped a slice of the sky in enough detail to see the full structure, they were shocked. They expected randomness. They got architecture. The cosmic web is the largest known structure in the universe, and the voids it contains account for roughly 80% of all the volume in existence. So what is actually inside a cosmic void? Almost nothing, but almost is doing heavy lifting in that sentence. A typical void spans 100 to 300 million light-years across. If you somehow teleported into the middle of one and looked in every direction with the most powerful telescope ever built, you would see only a handful of faint lonely galaxies scattered at enormous distances from each other. The density of matter inside a void is roughly 20% of the cosmic average, which sounds like a mild reduction, until you remember that the cosmic average already includes vast stretches of interstellar and intergalactic space that are essentially empty themselves. Voids are the empty parts of something that was already nearly empty. If you compressed an entire large galaxy cluster down to the size of a marble and placed it inside a void scaled to match, that marble would have to travel for thousands of miles before encountering another marble. The void is not empty in the quantum sense, because quantum fields permeate all of space and virtual particles flicker in and out of existence, everywhere. But in any practical, physical sense, a cosmic void is the loneliest environment the universe produces. Matter doesn't want to be there. Over billions of years, gravity has been steadily pulling mass out of voids and stacking it onto the surrounding filaments, making voids emptier with every passing age. Voids didn't appear from nothing. Their origin traces all the way back to the first moments after the Big Bang, when the universe was a nearly uniform soup of hot plasma, nearly uniform but not perfectly so. Tiny quantum fluctuations, smaller than an atom, created infinitesimal variations in density across the early universe. Some regions had fractionally more matter, some fractionally less. Then gravity went to work. Over hundreds of millions of years, regions with slightly more matter attracted more matter still, pulling it from neighboring regions and growing denser. The regions that started slightly underdense lost matter to their neighbors, grew even less dense, and the process fed on itself. This is called gravitational instability, and it acts like a slow-motion economy where the rich get richer and the poor regions are steadily drained. The filaments and clusters we see today are the rich regions, accumulating the matter that flowed away from what are now the voids. The filaments and clusters we see today are the rich regions, accumulating the matter that flowed away from what are now the voids. It is a region that lost the primordial lottery by an infinitesimally thin margin and has been losing matter ever since. The seeds of every void in existence were fluctuations so small that if you were standing inside the early universe, you would not have been able to measure them with any instrument we have ever built. Voids are not static regions of emptiness. They grow.
As gravity continues pulling matter outward toward the surrounding filament walls, voids expand from within, their boundaries pushing outward as the walls around them accumulate more mass.
Smaller voids merge into larger ones over time, a process that leaves the cosmic web with progressively larger and emptier bubbles as the universe ages. This makes voids surprisingly useful to cosmologists, because the rate at which they expand is sensitive to the balance between gravity and dark energy. Dark energy is the mysterious repulsive force causing the universe itself to expand at an accelerating rate, and voids feel its influence differently than dense regions do, because inside a void there isn't enough gravity to counteract the expansion.
By measuring the shapes and growth rates of voids across cosmic history, astronomers can probe how dark energy has changed over billions of years with remarkable precision.
A void is, in this sense, a measuring instrument built by the universe itself. The Bootes void, one of the largest known, stretches roughly 330 million light-years across and sits close enough that telescopes have mapped it in some detail. When it was discovered in 1981, the astronomer who found it reportedly said that if the Milky Way had been located inside it, we wouldn't have known other galaxies existed until the 1960s. We would have looked out and seen nothing. The existence of voids, their sizes, their shapes, the way they cluster and connect, all of it is a fingerprint of the early universe's physics.
Run the physics of the Big Bang through a computer simulation with slightly different initial conditions, and you get a different cosmic web with different voids.
Run it with the conditions we actually observe, and the simulation matches what telescopes see with stunning accuracy. This means the voids we map today are direct echoes of quantum events that happened 13.8 billion years ago, stretched and amplified across cosmic time until they became the largest empty structures in existence. And because voids are sensitive to dark energy, dark matter, and the total mass-energy content of the universe, mapping them precisely is one of the most powerful tools cosmologists have for understanding what the universe is actually made of.
Current surveys, like the Dark Energy Spectroscopic Instrument, are mapping tens of millions of galaxies specifically to trace the void network across billions of light-years and billions of years of cosmic history simultaneously.
The loneliest places in the universe are, in a quiet irony, among the most informative.
There is something genuinely difficult to process about what a void represents. Not frightening exactly, but vertiginous.
If a civilization had formed on a planet orbiting one of the rare galaxies marooned inside the Bootes void, their night sky would be extraordinary in its emptiness. They would have their own galaxy, perhaps a handful of faint smudges at extreme distance, and then darkness in every direction stretching for incomprehensible distances. They would have had no way to detect the cosmic web, no evidence that the universe organized itself into filaments and clusters, because from inside the void, those structures would be too far away to see. Their cosmology would have been fundamentally different from ours, perhaps permanently. We happen to live in a relatively populated region of the universe, threaded by filaments and close enough to the Virgo cluster to see thousands of galaxies with a modest telescope. Our understanding of the cosmos is built on that luck. The voids remind us that the universe contains places where the evidence for its own structure is absent, and that our view from here, crowded and rich with information by cosmic standards, is not the only view possible. The universe built vast rooms and left them nearly empty, not as an accident, but as an inevitable consequence of the same physics that built everything else. Emptiness at this scale is not absence, it is structure.